In this video, we will now visit our second notion of measure of randomness. Namely, we want to find out what is the least number of bits L. Least number of bits L such that if I give you a uniform random variable on L bits, so if I give you L independent coin tosses which are unbiased, then you can find a function f such that you can generate a given distribution P using this U. So P of f of U is close to the given distribution P. Okay, it's close in this total variation distance epsilon. So what is the minimum such bits required? This is the number of bits required to generate this random variable, and we will think of it as a measure of randomness in this random variable. This is sort of the complementary definition to the one that we saw in the previous video. Okay, so this problem is very much related to the one we saw last time. And rather than I'll just directly jump into the scheme. The scheme is very much like the scheme we saw last time. Okay, where last time what we did was we were given a random variable of a given distribution and we want to generate uniform random variable out of it. What we did was we divided the domain into small parts such that each part had roughly same probability. Some mass was left and that we dumped into this final part which we were calling xm plus 1. But the first m parts were balanced, they had roughly same probability. Therefore, if you declare different values on these different parts, that random variable is almost uniform, and we showed this formally. And what the amazing part about the scheme was what was the number of bits that we were able to extract? Well, it was the entropy of the random variable. Okay, so now we will look at a complementary scheme where we are given uniform random variable and we want to generate a PMFP out of it. This is something which may be very important in practice. You may have seen similar questions, but in a probability course where you use the inverse of the probability cumulative distribution function to do this. But what we will do now is very different. We are accounting for the number of random bits used. Okay, so here is a scheme. We define this set. This is a new set T lambda that we are defining. It's different from the previous one. Define this set, okay? Unlike the previous one where we had a large probability lower bound on minus log px, this is your P, the one you want to generate. Suppose lambda is a large probability upper bound on minus log px, okay? So this is my set T lambda, this one, and we assume that T lambda has large probability. So you can very easily check that for each x in T lambda, Px is greater than equal to 2 to the power minus lambda. Okay, so what we do is we set m to be greater than 2 to the power lambda, the same lambda here, and now we consider a partition of 1 to m. So since each probability is greater than 2 to the power minus lambda, we can say something about the cardinality of this set. Okay, so if you sum all the elements of this set, the probabilities of all the elements, that sums to 1, and that must be less than equal to, the probability must be less than equal to 1. But each element has probability more than 2 to the power minus lambda. Therefore, there are at most 2 to the power lambda elements in this set. Okay. So consider a partition y1 to ym prime plus 1 of this 1 to m set such that m prime is equal to 2 to the power the cardinality of T lambda. So remember, cardinality of T lambda is less than equal to 2 to the power lambda. Why? Because each element has probability at least 2 to the power minus lambda and probability sum to 1. So the total number of elements in T lambda cannot exceed 2 to the power lambda. So this m prime that we have is less than m by our assumption. Okay, we assume m is greater than 2 to the power lambda. Therefore, you can form this partition of 1 to m of size m prime plus 1. Okay, such that what do we want out of this partition? What we want out of this partition is, if you take any element x, remember there are m prime elements in T lambda. What we want is that each part has probability that is between pxi and pxi plus 1 by m. Okay, so the question is, why can we do this? Okay, or how can we do this rather? So take each element. We know that each element has probability greater than 2 to the power minus lambda, and 1 by m is smaller than that. Okay, So you just basically take one element and and these parts here, this probability is under a uniform distribution. Okay, so this is just the size of the number of elements you will take here, that number divided by m prime by m, which is more than to the power lambda. So you can convince yourself that this kind of partition y1 to y m prime plus 1 can be designed. Okay, it's just a very simple account keeping. Okay, this u is the uniform distribution. Okay, so now this is what we have done. We have constructed these parts as many, just one more than the number of elements in T lambda, just one more. And each part has probability. For the first m prime parts, the probability is between the probability of elements here plus 1 by m. Okay, so we roughly have these we roughly have these parts which have probabilities of these elements. So now you can imagine what we are trying to do. Whenever we see something in this part, this yi, we will declare xi. That because we want to generate something from PMF P. Okay, and it is off by some 1 by m, but that's the error we have to account for. Okay, and this last element x m prime plus 1 is something outside the T lambda, some arbitrary element you can choose. Okay, now what is our function? The function that we want to use to generate our PMF. Well, it's very simple. When you see y in yi, you declare xi. That's our function. So let's analyze the total variation distance between the generated output and the target distribution. So this is the generated. Sorry. So this is the generated, and this guy here is the target distribution. And they're close, that's what you want to say. So for each element x in T lambda, probability that you output that element minus the probability of that element under this distribution P. Okay, this differences we'll compare and claim that this is small for summed over all elements. And then, well, this function never declares anything outside T lambda. The only thing it declares outside T lambda is x m prime plus 1. So, but that we account for in the error here. And then this y m prime plus 1 final part, that also we account for error here. You can validate, you can check this bound. Okay, so we'll bound each of this term now. Okay, so for the first term, each of these elements, what we notice is right. So let's analyze each of these terms. So for the first term, that's how we constructed the set. This yi minus pxi. Remember that yi minus pxi, this is the condition, the green one here, is they differ by just 1 by m. That's how we constructed yi. Okay, so this is at most 1 by m for each part, and there are m prime elements in t lambda, and that's just m prime by m. The first term is easy. Third term is just this guy. Okay, so remember what is the third term? Third term is this guy. So for the third term, so this is the last term here, it requires some thought. Okay, so what we have seen is that for each xi, this is less than this. That's a construction of this partition. So we already have this bound for the first term. And now we sum over all of these guys. So you get p of t lambda there. And what do you get here? You get the first m prime parts. But remember that we have partitioned the whole 1 to m into just this m prime plus 1 parts. So this is just equal to 1 minus p of last part under uniform distribution. Correct? So this guy here, we can check from this one, is less than equal to 1 minus t lambda complement, probability of that. Okay, so by our assumption, this is less than equal to epsilon. So what we have shown is that this total variation, so this is t lambda complement one part, and then another one of such thing. So there were 2 times that. When you divide by 2, what you get is this is less than equal to this by this, and then you substitute that. This I put a question here for you to think about. Maybe you can pause and think about, because I'll answer this question right away. So remember that our construction tells us that each element in T lambda is this, and from that we verified this earlier. Let me reiterate that proof. So if for this is true for all x in T lambda, so if you add the probability of all the elements in T lambda, this probability must be greater than the cardinality of T lambda times 2 to the power minus lambda. But this sum here must be less than equal to 1, because probability sum to at most 1, and therefore T lambda must be less than 2 to the power lambda. So you get this bound. And you can choose any m of your choice. We choose m to be this guy here. This is a choice of m. And when we substitute this, what we get is that this is less than equal to 3 by 2 lambda. So the m is the number of bits, the size of the uniform random variable that we used. Okay. So what have we shown? Here is the theorem that we have shown. We have shown that suppose that you can find a lambda for which minus log px is less than equal to lambda with probability greater than 1 minus epsilon. So it's a large probability upper bound on this minus log px. This is the quantity we have been playing around this week and also last week. Okay, so suppose that is true. So this is related to your PMFP. This lambda which gives this bound is associated with your PMFP, the one you want to generate. Then if you use L equal to lambda log 1 by epsilon bits, that's just log of this guy, log m. Okay, lambda log 1 by epsilon bits. Then if you generate a uniform random variable with this length, or if you generate these many random bits, then you can find a function f, the one we specified above, such that the total variation distance between fu and p is at most 3 by 2 epsilon. So this is the number of bits needed, roughly lambda. Now, once again, what is a good estimate for lambda? Earlier we had large probability lower bound on this. Now we need large probability upper bound on this. Well, that's a good estimate is the expected value of this guy, which is the same guy, which is the first character of this course, namely the Shannon entropy. So once again, and in this particular case, you just want a large probability upper bound on a non-negative random variable. You can use Markov's inequality if you like to get this. But once again, even in this different question, the answer is the same. It is the Shannon entropy. Okay. So how many random bits do you need to generate a single sample from PMFP? Well, roughly HP bits. Okay. This is the sort of the third interpretation of entropy we have seen. So there is a saying, an important quantity has a habit of showing up in various contexts. And this HP keeps on showing up in different contexts, in different problems as an answer to different problems. And therefore it must be an important quantity. And we will see this throughout this course. In the next lecture, in the next video, what I'll elaborate a bit, next video is the last one for this week, and what I would like to elaborate on in that next lecture is this set T lambda. This set T lambda which comes up here. Okay, this is one kind of T lambda, the set of x such that minus log px is less than equal to lambda. In the previous proof, we had seen another set where minus log px was greater than equal to lambda. These sets, I am calling them typical sets because these are sets of large probability. So this is a typical set of sequences which are more likely to occur, the set which is more likely to occur. And we will study these sets a little bit. This so-called typical sets are very important in information theory. And if you look at any book on information theory, there are several excellent textbooks. They somehow build around different kind of typical sets. So just to give you an example, the famous textbook by Cover and Thomas, it defines typical set using law of large numbers. I hope you're reading the textbook on the side. The other famous book on this topic is by Chester and Kerner, that defines typical sets using the so-called method of types. And the third very interesting book on this topic is by Tae-Sun Han, and that uses the so-called information spectrum method, which is where I'm drawing most of my lectures from. That book uses another notion of typical set very similar to the one we have. Okay, so this defining this typical set is central to all the proofs that we have been seeing. So in the last part of this week's lectures, I would like to talk a little bit about these typical sets. Okay, so see you in the next lecture.